Hi everybody. Well, now that we are through with understanding functions, it's now time to move ahead with understanding of a specific type of a function. Everything related to functions is there with us, right? So a specific type of function is what we have to now study. Now, how does function of this type is a matter of study for us, and why is it like that? We need to know first that the article that is under our consideration is binary operations. Now here right now the article has no concern at all with function. You can see there is no terminology which is functions. Still I am saying the concept of functions is what is used in understanding of the binary operations. So binary operations are operations which are binary. That means operations which are binary means what? What is binary? Binary represents the number 2. Those operations, those tools which combine two elements to create a new element are called binary operations. What did I say? Those operations which combine any two elements to create a new element are called binary operations. From our former classes, we have studied about addition, subtraction, multiplication, isn't it? Division. What were they? What was the job of the operation of addition? Addition basically combined two distinct members, two distinct elements, two distinct objects, two distinct numbers. It combined them with this operation to create one single new element a plus b. What did subtraction do? The operation of subtraction again combined any two elements together with the help of this operation and created a new element a minus b. What was the job of the operation of multiplication? It also combined any two numbers. It combined two numbers with the help of multiplication operation to create one single number. And similarly, when I talk about division, division also used two numbers. Division also used two numbers, specifically this b. One of them is non-zero, right? So division also used two numbers. It combined them by the operation of division to create a new number a by b, where b is non-zero. So what basically I am trying to say is that suppose I give you the task of adding 2, 3 and 7. I am giving you the task of adding 2, 3 and 7. Can you add these three at one time? No. Addition at one time can act only on two members. Either these two you will add, or these two you will add, or first and third you will add, but at one time you can only add any two. Addition at one time can be applied to only two objects. So suppose I add these two, I get 5 plus 7. Now I add these two, which is this. What I am trying to say is, suppose there are 100 numbers which need to be multiplied. Then multiplication is an operation which at one time can act only on two members. So if there are 100 objects, 100 numbers to be multiplied, you can at one time pick any two to multiply, then get the result, then any two to multiply, get the result, then any two to multiply, get the result, like that. And therefore after many steps you will be able to obtain the actual answer of multiplication of those 100 numbers. But you will have to apply multiplication operation again and again and again and again. Why? Because multiplication operation at one time can be applied to only two members. Fine. And there are 100 members sitting. So 2, 2, 2, 2, 2, you will be just collecting all the pairs and you will be keeping on multiplying and hence getting the result. Same is the case with addition, same is the case with subtraction, right? Why is that so? It is because these 4 operations are actually binary operations. At one time they can only act on 2 distinct elements, or 2 same elements also. You can add 2 plus 2 as well. But on one time they can act on 2 elements only. These operations are what are called binary operations. What is their job? You've understood? Their job is to combine 2 members at one time to create a new member. They can combine 3 members also, they can combine 100 members also, they can combine 2 lakh members also, but at one time they can only combine 2 members out of the given ones to create a new member, which is if it is combining, if the operation is of addition, it is going to combine 2 members by addition operation to create a new member a plus b. If the operation is subtraction, it will be combining any 2 members with this operation to create a new member a minus b. If you have multiplication as your operation, it will be combining 2 members with the operation of multiplication to create a new member which is a into b. And if it is division operation and you have 2 numbers out of which one is non-zero, in that case it will be combining those 2 numbers like this by dividing a by b to create a by b as the new number. Fine. So the primary purpose of binary operation, you have understood that they basically are used to combine any 2 members to create a new member, and at one time they can only combine 2 members because they are binary. Cool. Now the point is, these are some binary operations that we are already aware about. What we were not aware about was the terminology that these are called binary operations because of the behavior that they exhibit. Okay. The point is, why are we doing it in the section functions? How is functions going to help us in understanding of the binary operations? For that, let me talk about an example. Consider addition operation on the set of natural numbers. Consider addition operation on the set of natural numbers. Now understand one thing. Addition operation on the set of natural numbers, is it a binary operation? If I pick up any 2 natural numbers, and if I pick up any two natural numbers a and b, is it possible that they can be combined by the addition operation to create another new natural number? A is a natural number, b is a natural number. If I combine a and b by plus operation, I know the usual addition is the meaning of this plus operation. Then a plus b again is going to lie inside the set of natural numbers only. Fine. So what I am trying to say is that addition operation on the set of natural numbers is very much a binary operation, because what is addition doing? It is picking up 2 members at a time from the set of natural numbers, adding them to create a new natural number. Okay, so what is happening is a, b, these are 2 natural numbers and they are being operated by the addition operation to create a new natural number a plus b. So at one time I can pick up 2 natural numbers, addition operation will be acting upon them, both of them, to create a new natural number a plus b. This is the statement which is giving you an idea, a signal to perceive binary operation as a function. What can I do? You can see that addition operation is a binary operation on the set of natural numbers. Means that at one time it needs 2 members, exactly 2 members to act upon to create one single member a plus b. So that means if addition operation can be acting upon, addition operation can act upon 2 members at one time, here I need 2 members and here there will be one single member, right? Addition operation is acting on 2 members to create one single member. So here I have 2 members and here I have 1 member. Can I say having 2 members is same as being represented by the ordered pair a comma b? ordered pair A comma B. If I say that addition operation is acting upon this ordered pair, that means it is acting upon A and B to create A plus B. Just a representation of two natural numbers is through this ordered pair having two components, first and the second. Is that understood? So here I can say that this plus is acting on ordered pairs A comma B, where A and B are natural numbers, to give me a single natural number A plus B. Here I need two natural numbers, here the result will be one single natural number. Here I will be having A comma B coming from n cross n, and here I will be having the single natural number coming from n. A and B are two natural numbers. I need two sets to represent the set of all two natural numbers. If I take the Cartesian product, that means I will be having inside this Cartesian product of n cross n all the ordered pairs with first and second components as natural numbers. So I can very well now say that this operation is acting as a function from n cross n to n, such that it acts upon every ordered pair A comma B in n cross n to create a natural number A plus B. That is what is this plus doing. So if you in a layman version, if you want to understand, you have this set of natural numbers. So many natural numbers are there, 1, 2, 3, 4, 5, 6 and so on. Addition operation is acting upon two natural numbers inside this set at one time. Any two natural numbers it is acting upon, it is adding them and creating a new natural number inside the set. To formalize this procedure, I am saying that this addition operation requires two numbers to act upon. These two numbers I am representing by an ordered pair, because ordered pair is going to require two numbers because it has two positions, first and the second. So first for the first number, second for the second number. So this addition operation is acting upon an ordered pair A comma B, where A and B are coming from natural numbers, to create a single natural number A plus B. And this has led me to the definition of this addition operation on the set of natural numbers as a function. I can say thus, addition operation on the set of natural numbers, can be considered as a function plus, from n cross n to n, because corresponding to each ordered pair I am getting a unique natural number. So each element in the domain has a unique image in the codomain under this operation plus, and therefore this plus is a function from n cross n to n, such that when plus is applied to this ordered pair A comma B, it produces A plus B. Plus is applied to A comma B is also perceived as A plus B. That you can see also as well over here. And thus, this is how you talk about binary operations on a set. A binary operation on a set is nothing but a function from that set cross that set to that set. So that when you pick up any two members from the set, this operation acts upon those two members and creates a new member in the same set. Or I can say that a binary operation associates every pair of members in the set to a unique single member in the same set. Because associating an ordered pair to a single member is same as associating two members from a single member. Clear? This is the aspect in which binary operation is related to functions and is understood as a function. So not just addition operation on the set of natural numbers is a binary operation, but first question says, for 1 mark, let R be the equivalence relation in this particular set given by A comma B belongs to the set R provided 2 divides A minus B.
That means A is related to B if and only if 2 divides the difference of A and B. Write the equivalence class of 0, where 0 is one of the elements sitting in set A. What is the equivalence class of 0? Equivalence class of 0 is actually the collection of all those elements belonging in set A which are related to A under the relation R. Which all elements in set A are related to 0? A over here is 0. Equivalence class of A is all those B belonging to A which are related to small a. Right now small a is 0, so all those elements of small a which are related to 0 under the relation R. This means all those B belonging to A such that B is related to 0, that means B comma 0 belongs to R. B comma 0 belongs to R because A is related to B under the relation R if and only if A comma B belongs to R. That means I want all those elements in set A such that B comma 0 belongs in R means B comma 0 will belong in R if and only if 2 divides B minus 0. So, such that 2 divides B minus 0. Only then B comma 0 will belong in R by the definition of R. Which are those A's such that 2 divides B minus 0? Let's try and see. Elements in set A such that 2 divides B minus 0. Elements in set A are 0, 1, 2, 3, 4 and 5. 0 minus 0. 2 divides 0 minus 0? Yes. Then 1. 2 divides 1 minus 0. Does 2 divide 1? No. So 1 cannot come inside this set. Then 2. 2 is one of the elements in set A. 2 divides 2 minus 0? Yes, 2 divides 2. So 2 is going to come over here. Another element is 3. 2 divides 3 minus 0. That is 2 divides 3? No. So 3 will not come over here. Next is 4 in set A. 2 divides 4 minus 0. Yes, 2 divides 4 minus 0. So 4 is going to come here. I want all those elements of set A such that 2 divides that element minus 0. Then you have 5. 5 is in set A. Does 2 divide 5 minus 0? No, 2 does not divide 5 minus 0, that is it. And so this is the set of those elements of set A which are related to 0. 0 is related to 0 under the relation R, 2 is related to 0 under the relation R, 4 is related to 0 under the relation R, and therefore inside the equivalence class of 0 lies those elements of set A which are related to 0, and they are these 3 elements. So this is the equivalence class of 0. Next you have f is a function from collection of all reals to the collection of all reals. Defined in this manner, find f of x. Let's try and find, this is pretty simple, f of x. f of x is what? 3 minus x cube whole to the power 1 by 3. Right? Now f of this quantity if you take as y, f of y is what? 3 minus y cube whole to the power 1 by 3. Now replace it. Y is what? 3 minus x cube whole to the power 1 by 3. This is y cube. Its cube you need to take and then whole to the power 1 by 3. Carefully, very carefully. You can see these 3 getting cancelled. You are left with 3 minus x cube whole to the power 1 by 3. This eventually comes out to be 3 minus 3 plus x cube whole to the power 1 by 3 plus 3 minus 3 cancels out, x cube to the power 1 by 3 which is x. So actually x means identity function applied on x. So FOF, basically FOF of x is coming out to be identity function on x. So over here FOF is nothing but identity function on the collection of all reals. That is what is the domain. So here FOF is coming out to be identity function. Clear? Next we have, let's start from R cross R to R given by A comma B goes to A plus 4B square be a binary operation. Compute minus 5 star 2 star 0. So star's definition is given to you. They are basically saying that A when operated with B under the operation star actually gives you one single element like this by combining A and B in this fashion. Is it understood? A and B are real numbers. I am being set to compute minus 5 star 2 star 0. This is what? Minus 5 star. Keep it as it is. 2 star 0. 2 star 0 is 2 plus 4 times 0 square by the definition. This gives me minus 5 star 2 because this is 0. Minus 5 star 2. Minus 5 star 2 is minus 5 plus 4 times 2 square. This gives you minus 5 plus 16, that is 11. So when you operate minus 5 star 2 star 0, the one single real number which pops up as the answer is 11. Next question. If star is a binary operation on the set Q of rational numbers defined as A star B as AB by 5, write the identity element for star if any. Now they are already saying that this is a binary operation, so you don't need to verify it. Under this binary operation you need to talk about the existence of the identity element. I am saying let E be the identity element. Let E be the identity element in Q under star. Under the very operation star inside the set of rational numbers, suppose E is the identity element. I don't know what the value of E is. What is the role of identity element? To not change the identity of any particular rational number inside this set under star. That means any rational number when operated with this element E does not get affected. The identity of any element does not change when it is operated with the identity element, and this is true for every rational number because right now the set in concern for us is the set of rational numbers. This implies A star E is A for all A in the set of rationals. A star E is what? A star E is AB by 5. So it is AE by 5 equals A for all A in the set of rationals, which implies what? Clearly you can see this is AE equals 5A and therefore E is equal to 5. And 5 very much is a rational number. So the rational number 5 happens to be the identity element. Therefore, identity element is equal to 5, which is a rational number. Clear? Next we have, if this function given by fx equals x square plus 2 and g by x upon x minus 1, then find FOG and GOF and hence find FOG of 2 and GOF of minus 3. Whenever I am talking about FOG, this is defined from the domain of G, isn't it? FOG is defined from domain of G and GOF is defined from domain of F, right? I can say to collection of all reals, to collection of all reals. FOG is defined, let us first talk about FOG. FOG is defined only and only when range of G is contained in domain of F. And GOF is defined if and only if range of F is contained in domain of G. So first of all we need to talk about domain and range of F and G. Fx is given as what? Fx is given as x square plus 2. Clearly x is allowed to take any rational number, any real number, because x square plus 2 is a defined real number for any real number as x. You plug in x equals any real number, x square plus 2 will always give you a defined real number. So domain of F is clearly all real numbers. What about range of F? Well, x square is always a non-negative quantity for any real number. You know this. So x square plus 2 is greater than or equal to 2 for all x in the collection of all reals. That means x square plus 2 actually means this. Whatever you plug in place of x, x square plus 2 will always give you values in this interval, and that is what is the range. Range of F is 2, infinity. This is about F. G of x is x upon x minus 1. Clearly you can see this function refuses to give a real value when you put x equals 1. When you put x equals 1, you get 1 upon 0, which is not a real number. But apart from 1, if you put any real number in place of x, this quantity is giving you real number as the answer. And therefore domain of G is all real numbers minus singleton 1, And range of G, if I talk about, you know what is the drill? We put x upon x minus 1, that is definition of G of x equals y. Compute the value of x in terms of y. Right now it is y in terms of x. Now compute x in terms of y. You get y equals yx minus y, which gives you x, or let me write y equals xy minus x, which is x y minus 1, and therefore x equals y upon y minus 1, which also means this particular x is a well-defined real number only when y is not equal to minus 1. Just for y not equal to minus 1, rest all the values of y are giving me x as a real number. So this x is a real number only for y equals to not equal to minus 1. So range is also all real numbers minus the quantity 1. Now if I want to talk about FOG, FOG's existence, I need to ensure that range of G is contained in domain of F. Now range of G is this, range of G is actually this, and domain of F is collection of all reals. Clearly range of G is contained in domain of F. Range of G is contained in domain of F, which implies FOG exists. FOG is defined from the domain of G. So for x belonging to domain of G is what? R minus 1. We need to define FOG. For x belonging here, FOG of x is f of G of x, which is f of G of x is x upon x minus 1, f of G of x, and when you put it over here, f of G of x, that means x upon x minus 1 whole square plus 2. This gives you what? X square upon x minus 1 whole square plus 2, which gives me x square plus 2 times x minus 1 whole square whole upon x minus 1 whole square. That is, this comes out to be x square plus 2x square plus 2 minus 2x, so minus 4x whole upon x minus 1 whole square. This is x square plus 1 minus 2x, x square plus 1 minus 2x. So this is what you have. So you have 3x square minus 4x plus 2 whole upon x minus 1 whole square, and you are supposed to find FOG of 2. So therefore FOG of 2 lies in this set, 2 lies in this set. So FOG of 2, where 2 is coming from here, will be 3 into 2 square minus 4 into 2 plus 2 upon 2 minus 1 whole square. This is 12, 12 minus 8 is 4, 4 plus 2 6, 6 upon 1 is 6. Similarly, you can compute GOF. Now range of G is contained in domain of F. Now I need to show range of F is contained in domain of G. Range of F is this, domain of G is this. Clearly inside this only 1 is not there, and I need all real numbers beyond 2. So clearly all the real numbers beyond 2 are lying inside this set. So as range of F is contained in domain of G, this implies GOF is defined. GOF is defined from domain of F.